Okay, dear student, Assalamu alaikum. Uh, Now we will have a short discussion on the use of Norton Theorem or application of Norton Theorem in order to calculate the unknown quantities given in a question. Now, let's take up an example. We are given a circuit diagram, in which case we are asked to find out V naught, which is a voltage across 1 ohm resistor. We have to apply Norton theorem. The steps are 4 in number again, and they are rather very similar to Brillent theorem, except with a little difference. So let's have the steps one by one. The first step is to mark terminals A and B across element of interest, that is, in which element you are going to find out the electrical quantity. In this case, it is the voltage. Now, in this first step, then remove this element from the terminals A and B and do not leave them open. In this case, we have to apply a short circuit across A and B, so that you will be expecting a current. Now, this current is IAB, which is in fact the Thevenin current. So Norton current. This IAB is the Norton current IN. Now, our objective is to convert this circuit with respect to terminals A and B into this simplest possible circuit, which contains a current source in parallel with an impedance Zn. Now, this current source is a Norton current source. This is the Norton equivalent impedance as viewed from open terminals A and B. So our first step is complete. Now let's go to the second step. The second step is to calculate this current flowing in the short circuit. For this purpose, it is better to use KVL rather than KCL. So we have to identify loops. There are 4 loops, 1, 2, 3 and 4. But we have to be careful. We have to try to assign only one of the loop current with the current source as well as the short circuit, so that our calculations becomes easier. Now, in this case, we will go for I1 in this loop. Then this loop will contain I2. Then we have this loop, which is having a current I3. And finally, we have this whole big loop, which is constituting a current I4. Now, if you look at the loop currents, we have I2, which is known current, and this is equal to -2 amperes, because the I2 direction is opposite to the current source direction in this branch. So it is -2. So one of the current is known, so the number of equations are now reduced from 4 to 3. Now similarly, I4 by definition is the short circuit current IAB, which is in fact the Norton current IN. That is what we are interested in to build up the Norton equivalent circuit. Now still we are on the second step. So let's have the loop equation. The first loop is this contour, which contains 6 volt source minus J1 capacitive reactance and 1 ohm resistor. So this current I1 is coming out of the negative terminal of the 6 volt source. So we have -6 there. So we have -6 equals to now minus J1 into I1. This is the first drop. Then the second drop is this one, in which there are 4 currents simultaneously running in the same direction. And this is I1 plus I2 plus I3 plus I4. Now, in this case, this current I2 is known. So we replace it with the known current, which is -2. Now, if we simplify the equation, our loop equation then becomes -4 equal to 1 minus J1 into I1 plus I3 plus I4. This is our equation 1. Now this is the first loop. Now the second loop is this one, which contains I2, but I2 is known, so we need not to form the loop equations. Now the third loop is this one. If you look at the contour, this is the third loop. Now mind you, the current is I3, but it is coming out of the negative terminal in this case and positive terminal in this case. So we go for -6 plus 12. These are the source voltages. Now the drops are J2 into I3 plus again the next drop is due to the 1 ohm resistor, in which case we have simultaneously 4 currents flowing in the same direction. Again, this I2 is known, so we simply replace this by its value, which is -2 ampere. So if we simplify this one, it is 8 equals to I1 plus 1 plus J2 into I3 plus I4. This is equation 2. Now finally we have the last loop, which is actually the outermost loop, which you can see along the contour. I am just having the last loop, which will complete our second step. So in this case, if we build up the loop equations in the same manner and simplify, we will get 8 equals to I1 plus I3 plus 2 times I4. This is equation 3. Now let's arrange them in the matrix form. So we have -4, 8, 8, and then we have the square matrix. That is for equation 1. For equation 2 we have the coefficients. I1 coefficient is 1 plus J1 plus J2 is the coefficient for I3, and 1 is the coefficient for I4, and lastly we have 1, 1 and 2. So we have the currents I1, I3 and I4. Now likewise, using Kramer's rule, we can find out the unknown quantity, or the quantity we are actually interested in. We are interested in, remember, the quantity I4, which is IAB, the short circuit current, and this is in turn equal to the Norton current. So let's find out I4. For this purpose, we need the determinant of the square matrix according to Kramer's rule, which is evaluated as 4 plus J1. And then we need delta 1, which is the determinant of the cofactor matrix for, delta 4, which is the determinant for the cofactor matrix to find out I4. So we have delta 4 is determinant of the cofactor matrix for I4, which in this case is we have to replace the last column, that is the I4 column, with this column vector 8, 8. Now if we take the determinant of this one, so the determinant delta 4 comes out to be 16 plus J24. Now finally I4, which is equal to IN, that is the short circuit current, is delta 4 divided by delta, which is 16 plus J24 divided by 4 plus J1, and this comes out to be 5.17 plus J 4.7. So this quantity is now known, that is one parameter of the Norton equivalent circuit is known. Now let's work out the second parameter, which is now our third step. So the third step in this case is to find out the open circuit impedance with respect to terminals A and B. So what we have to do now is to leave this open circuit, and then the rule is to short circuit all the voltage sources as in the Thevenin case and replace the current source with open circuit. So the open circuit, the current source, let's get rid of all the currents over here so that it doesn't look like a junk over here. So we have the situation on board, which is this one. Now what we see over here, now if we look into the terminals A and B, we have three impedances in parallel, that is one in parallel with minus J1 and this is in turn in parallel with J2. Now the combination is then in series with this 1 ohm resistor. So this will give us ZAB, which is equal to the Norton equivalent impedance, and if you calculate this one, this comes out to be 1.8 minus J 0.4. So we have obtained the second parameter of the Norton equivalent circuit, which is the Norton impedance. Now the Norton circuit is complete. So in the third step, we have calculated the Norton equivalent impedance. The third step is complete. All we are left is the last step, step number 4, in which we are going to find out the quantity required in the question. Now in question we have the quantity which is the voltage V0. Now if we reconnect the removed 1 ohm resistor across the Norton equivalent circuit, we have a single node over here. If we call this one as a ground node. Now remember, the node voltage is same as V0, so this becomes easier. So the current moving towards the node is this one. Then we have current moving output from the node. This branch current is V0 divided by 1.8 minus J 0.4, and then we have V0 divided by 1. So all you have to calculate over here is V0. So V0 is equal to 3.6 plus J 2.8. And if you convert this into the polar quantity, polar form, we have 4.56. Angle is 37.87 degrees volts. So this is the final answer. So you go through this lecture clip and also go through the lecture notes in order to make sure that you understand the use of Norton theorem. Thank you very much.